We move to the last part. Okay, this is the Laplace transform. Yes. Again, this is a chapter in your book, chapter 6, but here we will only address few concepts only, not the whole chapter. Basic concepts. Okay, so these concepts that we will address are going to be, number one, why do we need another transform? Okay, from a signals and systems point of view, not from a mathematical point of view, but understanding that requires a little bit looking at the mathematical and then how to calculate that transform. Okay, and its inverse, similar to what we did with the Fourier transform. So we discussed how to calculate the Fourier and its inverse. Okay, these are the two things that we really need to discuss today. So why do we need another transform? Okay, what are the advantages of having this transform compared to the existing ones? What does this transform represent? All of these falls under the first question, and then the second question, okay, I know why I need it, how can I calculate it? That's the second part, okay? And they're actually interlinked. So while describing one of them, we probably explain almost everything that we need to describe for the second part, and then when we go to the second part, we just highlight what we have already discussed, okay? Similar to what happened when we were discussing sampling theorem, and then we touched upon the reconstruction. We almost actually figured it out, but again, it needed to be highlighted later on, okay? So let's go to why. And to answer the question, why, okay, we need Laplace transform. To answer this question, there are two reasons that I will mention. One of them has to do with just pure mathematical situation, and the other one is more into systems understanding. Okay, so the first part, remember that for the Fourier transform, okay, for Fourier, we had a condition that if x, the integration from minus infinity to infinity, x of t dt is smaller than infinity, which means it's bounded, which means that I have a finite energy signal, right? We can find, okay, x of omega. We can find our Fourier transform for this signal. Otherwise, we can't. And an example that we did for that a couple of lectures ago is when we had this signal. So example of where you cannot find a Fourier transform was this signal, e to the a t unit step of t, where a is a positive number. Okay, for that signal, if you want to calculate the Fourier transform, you will go through this integration, right? So to find so if this is my x of t, right, then my x of omega in this case is equal to the integration from minus infinity to infinity, x of t e to the minus j omega t dt, and then you substitute. When you substitute the unit step, your integral becomes from 0 to infinity only, because the negative side is equal to 0, so it's not part of the integration. And then in that part from 0 to infinity, you have the e to the at multiplied by e to the minus j omega t dt, and this is equal to the integration from 0 to infinity e to the minus, and then you have a plus j omega t, and you integrate with respect to t. No, sorry. Without the minus. Right? And inside, you have the minus. Yeah. Okay? E to the a minus j omega, and the whole thing is multiplied by t. And we notice that this is a sinusoidal signal. E to the j omega t is a sinusoidal signal, right? Positive or negative, it doesn't matter, it's just a phase shift in that sinusoid. And it's multiplied by e to the at, which is a growing exponential, right? Now the problem is, this is something that we cannot calculate at infinity. It will either blow out because the amplitude keeps growing, or even if the amplitude was constant, I don't know exactly what a sinusoid looks like at infinity, right? Sinusoid, does it go up or down or zero, negative or positive? I don't know. It just oscillates, and I don't know what happens to it at infinity, because there is no such a thing like a fixed place called infinity, right? And not only that, in this case, it's growing actually, so it's multiplied by e to the at, which is a growing exponential, when a is a positive number, so I know for sure it will blow out at infinity. So I cannot find a Fourier transform for this signal. The Fourier transform blows up. I cannot calculate it, right? So that's an example. We'll see later on that using the Laplace transform, we can actually find a frequency representation, because why do we do the Fourier? We just want to look at this signal in frequency domain. Using Laplace, we can look at this signal in frequency domain, and we'll see in a minute how. Okay, that's one reason. Okay, the other reason is, okay, for systems very similar, but from a systems point of view, that are unstable, or we don't know about their stability, we can, at R, let's say this is number I, and this is number double I. We can, for I, find their frequency domain representation, and for double I, investigate their stability properties, and even find how to change their design to become stable. Right? It's called stabilize the system. And we will see this as well. So, in a nutshell, it allows us to investigate situations from a signal and a system's point of view in frequency domain that were not possible to investigate using the Fourier transform. Okay, so that's why we have the Laplace transform. It extends our ability to investigate in frequency domain. It addresses situations that were not mathematically addressable using the Fourier transform. Okay, how does all of this happen? Requires us to look at the second part, which is how do we calculate that Laplace transform, and then accordingly figure out why it has those nice properties. Okay, so let's look at how to calculate, how to find Laplace. Of course, as a mathematical calculation, you have already studied your Laplace transform in math. right? And you have used it mainly as a tool that allows you to solve homogeneous linear differential equations in a very simplified algebraic approach, right? You no longer needed to integrate or to investigate general particular solution or do this or do that. You just convert your differential equation into algebraic equation in S, the Laplace transform variable, and then you solve for the values of S, and accordingly you can figure out immediately the solution, the typical exponential and cosine solutions to your differential equation, right? Well, that's nice. That's also useful here when we convert between time domain and frequency domain, but not in the sense of solving differential equations, more in the sense of investigating signal properties, system properties, particularly the stability property of systems, in addition to being able also to represent some cases that were not representable before in frequency domain. Okay, so how to find the Laplace transform? It's simple. The Laplace transform itself extends, so it extends the frequency domain from just the j omega to a complex sigma plus j omega, okay, which is called S. This is our complex frequency. So we used to deal with a single dimensional frequency, omega, which is a real frequency, and that's it. Okay? It's multiplied by j, but it's a real frequency. Okay? Now we have a two-dimensional frequency that has a real part, sigma, and an imaginary part, omega. And typically, the sigma part represents real growth or real decay, and the j omega part in the exponent of an exponential represents the oscillation, the variation with respect to time in a periodic way, right? So that's just to keep it in mind, but both combined, we call that the complex frequency S. And based on this, you can expect the following. The definitions of the Fourier transform are very similar to the definition of the Laplace transform in terms of the mathematical representation. We will see that now. The properties of the Fourier transform are very similar to the properties of the Laplace transform. So whatever you studied about the Fourier, for example, multiplication in time is convolution in frequency, and convolution is time is multiplication in frequency. The same happens for the Laplace. If I differentiate a signal in time domain, this is equivalent in frequency domain multiplying its Fourier by j omega. If I differentiate a signal in time domain, this is equivalent in Laplace domain multiplying its Laplace transform by S, which is again the more extended version of j omega, and so on. So those properties correspond to each other, and we'll see in a minute that actually there is a way to get always the Fourier transform from the Laplace, because the Laplace is the more generalized form. So taking that into account, we define the Laplace of a signal x of t, which is what we call by definition x of s, is equal to the integration from minus infinity to infinity, our time domain signal multiplied by e to the minus st, and we integrate with respect to time. Okay? So same like the Fourier, but we just removed j omega from there, and we replaced it by s, which is a complex representation, sigma plus j omega. Okay? The problem, and again, in some cases, you can actually use this definition to find x of s from x of t with the tools of math that you have studied so far. The problem happens on the other way. Remember, there is always an inverse transform. So L minus 1 of x of s. If I have the Laplace of a signal and I want to find its time domain, x of t, then this is equivalent to the integration. I'm not going to write the limits of the integration now because they will look scary, but I will explain what they mean. X of s multiplied by est, and you integrate with respect to s. Now the problem is our integration variable for the first time here is a complex number. All the integrations that we did for the Fourier, and even the integration that we did here for the Laplace calculation, we were integrating with respect to either t or omega, and all of these are real values, right? Now for the first time, we are integrating with respect to a complex s, which has a real and imaginary part. Solving this integral falls into what I mentioned earlier in some of the cases of the Fourier transform, right? So it falls into the complex analysis domain of mathematics, which is something that most of you, if not all of you, have not studied, neither in college nor before in high school, okay? And the methodology of solving this is called a contour integral. And again, you haven't studied that, so don't worry about it. I will write the limits and I explain what they mean, but before doing that, the fact that you cannot solve this integral means simply that in all cases where you will be asked to find an inverse, you will have to use table and properties. So you have table of famous Laplace transforms and properties, and you will use that to figure out what was your time domain signal or calculate the inverse. Similarly, by the way, even in calculation of the Laplace itself, 90% of the time is going to be table and properties, but again, in some cases, you can use the definition. Here, you cannot use the definition. For you, for more advanced mathematical people, they can, but they have to use other tools of math. I will just mention here the limits of the integral. Interestingly, they are sigma minus j infinity and sigma plus j infinity. What does this mean? Looks very strange, right? Well, if this was omega, if this was the Fourier, what did we do for the Fourier? We were ranging our omega from minus infinity to infinity, right? Now here, when we made this complex, we still, in this integral, are ranging our omega from minus infinity to infinity. Don't forget that the S is equal to sigma plus j omega, right? So what this says is I'm still varying my omega from minus infinity to infinity, but I keep my real part as a single value. So I'm not varying the real part, right? This means what? If I draw this in the complex domain, what does it mean? Look at the complex domain. Bad color. Okay, this is the real axis, and this is the j omega axis, right? If I'm changing my j omega from minus infinity to infinity while keeping sigma at a certain value, this means that while doing my integral, the values that I cover are where? They are all values that belongs to some line parallel to the omega axis, right? So I pick all values across this, and this is a line that cuts the real axis at the value sigma, right? So here, when I'm doing this integral, I'm picking all possible values only on this green line, from minus infinity to infinity of the omega, and always my real part is fixed at a value sigma. This is why we call this a contour integral, because we are doing those, again, this is a contour if you assume that the plus infinity and minus infinity, they meet together, right? Anyways, it's the whole idea of contour is that we perform our integrations going through some line, whether it's a straight line or some wavy line or whatever, and typically they are closed lines. Okay, so we call them closed contour integrals. But anyways, doesn't matter to us that much. You don't need to worry about it that much. It just explains to you one important thing, that we still vary here our frequency across the whole range when we are calculating the Laplace transform. So we are covering the whole frequency range again, but we are giving our frequency another dimension called sigma. We are making it two-dimensional frequency. Why this is useful? Let's look at the example that we mentioned that it does not have a Fourier transform and see whether that example will have actually a Laplace transform. Because we said the e to the a t, when we try to calculate a Fourier transform for it, we couldn't. Can we do it in Laplace? Let's see. Okay. Any questions so far? No. Okay. So let's look at that guy, the x of t is equal to e to the at multiplied by unit step of t. That's my time domain signal, and see how can I get x of s. Can I actually calculate that? And if I can, what's the value? For this one, we will just use the definition. I told you, when you calculate Laplace, you can use the definition. You calculate the inverse, you cannot use the definition. Okay, so for this one we'll use the definition. So let's go for the definition. X of s is equal to the integration from minus infinity to infinity, x of t, which is e a t unit step of t multiplied by e to the minus st dt, right? And then for the unit step, I can say that I would start only from 0, right, up to infinity, and in that range the unit step is equal to 1, so it doesn't affect my integral. Don't forget that a is greater than 0, okay? So I have e to the at multiplied by e to the minus st, and I integrate with respect to time. This is equal to the integral from 0 to infinity, e to the minus a. Sorry. E to the, I don't know why always I do this. A minus s, right? T, dt. Okay? And solving this integral will give you what? 1 over a minus s, right? Okay? Multiplied by e to the a minus s t, and you have two substitutions, 0, infinity. The 0 substitution is nice. I can get rid of it because it's going to give me what? It's going to give me 1 here, right? If I substitute t equals 0, the whole thing becomes 1, e to the power 0. The infinite substitution is still a problem. But here I can solve the problem under certain conditions. And let's see why I'm saying that we can solve the problem here. So remember, a is greater than 0, right? Now let's open that s into the real and the imaginary part of it. Okay, so we end up with what? This is equal to 1 over a minus s. Leave the outside thing, doesn't matter to me. And let's open the inside thing. So e to the a minus, and then s is equal to sigma plus j omega, so j omega as well, right? Correct? So minus s becomes minus sigma minus j omega, okay? And the whole thing is multiplied by t, and I have to substitute at infinity and 0. The 0 case, anyways, we will leave it as is until we get to the point of evaluation, which is equal to 1 over a minus s, and then you have inside, the real part is a minus sigma multiplied by t, and this is e, right? So you have e, right, to the power. This is real and this is real, right? So it's a minus sigma, right, multiplied by t, this part. Correct? And then this whole thing is multiplied by e to the minus j omega t, right? Okay, let's look. Sorry? Yeah. And please, yes. Okay. And we have infinity 0. Now let's look at this. Remember we said that this complex exponential, when multiplied by a real exponential, we can find it at infinity under the condition that this part is decaying, right? Now when this part is going to be decaying, a is positive. So what is the condition on sigma to guarantee that this is decaying?
Sigma is greater
Then
than
a, not 0, a.
yes.
Sigma has to be greater than a, so that the whole thing here becomes negative and we have a decaying exponential, right?
Why you want it to be negative?
Because we want this to be decaying, so we can say at infinity it goes to 0.
Okay.
If it's not decaying, then at infinity it grows, right? If the sigma is smaller than a, then this is e to the positive t, and t goes to infinity, so it's going to be growing, right?
It should be a negative power.
Sorry?
Negative power.
Negative power. So sigma has to be greater than a, right? Okay. So the condition here, so if sigma is greater than a, then, okay, we can continue. So it's equal to 1 over a minus s, and then we can do the substitutions, right? When we substitute the upper limit, we get what? When we substitute infinity, we get what? 0. And we substitute 0, we get what? 1, right? Minus 1. Okay, upper limit minus lower limit value. Okay, which is equal to 1 over s minus a. Okay, but this is only possible if I choose my frequency range such that the real part of that s, of the complex s, has to be greater than a, right? We call this condition the region of convergence. Okay, or it's written as ROC. Okay, so our ROC, so the Laplace transform is 1, that's how we write it at the end, is 1 over s minus a with region of convergence sigma greater than a. So we always associate with our Laplace transform, we always associate when we can calculate this. We can only calculate this if we choose sigma greater than a. If you want to draw this region of convergence on the complex domain, how it would look like? Like, show me where is the region of convergence in the complex domain. How it would look like, Kabinet. Here is again your real axis, and here is your imaginary axis. And the region of convergence says that your sigma has to be greater than a. So again, the real axis here is the sigma, right? That's the real part of our complex exponential, and the imaginary axis is j omega, right? So when we say that our sigma has to be greater than a, so if this is the value of a, we are talking about this region. The region where sigma is greater than a. صح? Real axis, imaginary axis. Okay. So the real axis is the value of the sigma, and the imaginary axis is the value of j omega, because our S is composed of a real sigma and an imaginary j omega, right? The condition says that your sigma, the real axis, has to be greater than E. So the region of convergence is whatever on this side, regardless of the value of omega. Any value of omega is okay, but my sigma has to be greater than the value A. So that's the region of convergence. تمام؟ Any questions? طيب. Why does this? Okay, the two things. Number one, the Laplace transform allowed us actually to find frequency domain representation of a function that we were not able to find its frequency domain using the Fourier. Okay, that's number one. Number two, okay, it can allow us to do this, but under certain conditions. These conditions are represented by the regions of convergence always. And always a Laplace transform is not complete by only giving the expression. You have to give the expression and what is the region of convergence. In fact, for the same expression, like 1 over SA, okay, if you have a different region of convergence, and I will show you a quick example of that, the original time domain signal is different. Okay? Here are a couple of examples without going into the calculation, but quickly. If I have 1 over S minus A, and my region of convergence is this, the one that we just saw, right? So this is sigma, this is J omega, and this is A. So with region of convergence, sigma greater than A, your time domain signal is e to the AT u of t, right? And A is greater than 0. That's one example, okay? The same thing, 1 over S minus A, and your region of convergence is sigma greater than A, and sigma is less than minus A. These are, so that's like a union of those two region of convergence, which means that it would look like this. Here, and also here. This is minus A, and this is A. Tamam? So this and this, combined together, the union of those two, is your region of convergence. Okay? In this case, your time domain signal, very interestingly, is actually e to the AT and is greater than 0 without unit step. So this is an exponential, a growing exponential that goes in the negative and the positive side. It's a full growing exponential. The other one up there is a growing exponential, but it only starts at 0. It doesn't have anything on the negative side in time domain. Okay? And there is more. I mean, if you deal with negative a, so if a is a negative value, you will have other variations of the regions of convergence. Okay? So the regions of convergence is very important because it allows us to uniquely identify what's the actual Laplace transform and what was the original time domain signal. خلاص? Always, even when you look at the table of Laplace transforms, for each transform, there is a corresponding region of convergence. Okay? Another thing which is very nice to notice as well is, remember that the Laplace uses S, which is equal to sigma plus j omega. Fourier use only j omega. So if we try to look at the Laplace domain, sigma and j omega, if this whole two-dimensional domain is my Laplace domain, the Fourier is only this part of the domain. So you can see the difference between the generality of the Laplace, right? It can have a frequency, a complex frequency that can have any values in this whole two-dimensional domain, while the Fourier is only a single line in that domain. This is why the Laplace is a much more generalized representation. Okay, so simply, the Fourier is only when you substitute S equals j omega, and without any possible real value for sigma. Sigma becomes 0. Okay, so this is where you have your Fourier. This is the Fourier. Okay, domain.
Fourier from Laplace.
And this is how you find Fourier from the Laplace. Just simply remove S and put j omega in its place. Okay, while the Laplace domain is this whole thing. Right? All of this is the span of the Laplace domain. It's the two-dimensional domain here, while the Fourier represents just a single line in the Laplace domain. And yes, as you said, to find f, the Fourier of x of t, or let's try Fourier of x of t from the Laplace of x of t, simply set S equals j omega in x of s, the Laplace transform of the signal x of s. Just go to that Laplace transform and set S equals j omega. One last important comment, and I will finish today. Sorry, I took a little bit longer, but it only takes like a couple of minutes. Is related to exploring the stability of systems. Okay. Generally speaking, so system stability through h of s, the Laplace transform of the system itself. They call it the transfer function. This is called transfer function. Okay? Sure, definitely. So if you have the transfer function, typically the transfer function h of s, when you look at it as a function of s, and you have been through this also when you were solving differential equations, you will find that it corresponds to, for example, okay, s minus z1 times s minus z2 times s minus z3 and so on, divided by s minus p1 times s minus p2 times s minus p3 and so on. Okay, so it can be decomposed into multiplication. Sometimes some of those terms are second order. You cannot break them into a first order term, but that's okay. I mean, you have s minus p1 multiplied by another s minus p1, so it becomes s minus p1 square. But anyways, it's typically represented in this way. Okay, that's your representation of the system impulse response, h of t, when you take its Laplace transform. Okay? Now you notice what? That there are certain values of S, right? And by the way, the general values of those Z1, P1, Z2, P2, and so on, they are complex numbers. They don't have to be real. Okay? There are certain values of S that causes this whole expression to go to 0 when S is equal to Z1, or S is equal to Z2, or S is equal to Z3. This whole expression is going to go to 0, right? And there are other values of S that causes this expression to blow up, to go to infinity. If S is equal to P1, then you have a 0 at the denominator, which means that the whole the whole transfer function blows up. Okay. We represent this in the complex domain by something called the poles and the zeros. So these are poles, and these are zeros of your system. Okay, so we go to the sigma j omega, that's our S domain. So this is the S domain. Okay, the real and the imaginary part of your S, right? And at the value P1, let's say P1 is equal to 3 or maybe 2 plus J2, right? So the P1 is a complex number that exists here. So it has some real value and it has some imaginary value. That's P1. We also have P2, P3, and so on. So we have some, what we call the poles of the system. So P2, and maybe the location P3. The poles of the system, okay? And we have also the zeros of the system, but we don't care that much in terms of stability about the zeros. Now, sorry, let's say that this is where P3 is, okay? Now, if your system has poles with a positive real value, then this is an unstable system, okay? If all the poles of the system are in the negative real value, so they are in this part of the graph, then your system is stable, okay? So if all the poles, if all PI's, اللي هم البولز, are in the negative real half, okay, system is stable. Otherwise, if at least one of them, like what we see here, for example, P1 and P2, both of them are with positive, they are poles with positive real value, right? Then this is an unstable system. And by knowing this, we can actually stabilize the system. How do we stabilize the system? We change its transfer function by multiplying it by a 0 at this location and another 0 at this location. Why? Because now we guarantee that if if S takes this value, the 0 will cancel with the pole, right? Because we added a 0 at the same location. And also, if S takes this value, if I go in the frequency domain, and for some reason or the other, due to the input, the system response is going to be using this value of S, then the added 0 at that location is going to cancel the pole, so the response is not going to blow up. Okay? This kind of insight, we cannot see it in the Fourier transform. Okay? We can't see this kind of insight in the Fourier transform because the Fourier transform is going to be only on the j omega axis. Doesn't have any real part, so we cannot use it to test the stability of the system. In fact, any unstable system will not have a Fourier transform in the first place. Will not be able to calculate a Fourier transform for it. Okay? So that's another nice thing that you can see. We are not going to explore this too much because it belongs more into the control field, right? But people who study control, particularly I think electrical engineers, they will explore this a lot. But for us, you just need to understand the concept that stability can be detected from the existence of poles. If they are on the right side of that complex domain, then my system is unstable. If I want to think of the simplest way to stabilize, I'll just place another 0 above the pole to cancel each other. Full stop. Okay? Not more than that, and conceptually. So not really in terms of solving problems on this. That's too much. for you to solve problems on this, and that's what we will do next week. We'll just do some examples on this, okay? On the, not this, I mean on the Laplace transform to solve some examples. You'll simply be given a signal or a system in time domain, and you'll be asked to find the Laplace, or vice versa, given in the Laplace, and you'll be asked to find the time domain representation, okay? But not really solving control problems, okay? So don't worry. Just keep the concept. You might be asked about this conceptually only, but not really solving problems with this, okay? You are done. And the last thing to reiterate about both for the Laplace transform and the Fourier transform is the system response. System response to input. So remember, in time domain we have, if a signal x of t is put into a linear time invariant system with impulse response h of t, then the output y of t is equal to the input x of t convolved with the impulse response h of t. Same thing can be done in the frequency domain. So if I have an input x of t, that when we convert that to frequency domain, it becomes x of omega. Then if we also take the Fourier transform of the impulse response, we get the frequency response h of omega, and the output represented in frequency domain is called y of omega. Then in this case, y of omega is equal to x of omega multiplied by h of omega. So the convolution in time domain is replaced by a multiplication in the frequency domain, and we can get the output much easier. The same thing happens in the extended frequency domain, the Laplace. So we have the system transfer function, h of s, which is the Laplace transform of the impulse response h of t, and we have the Laplace transform of the input x of s, and we get the output in the complex frequency domain, or in the Laplace domain, y of s equals x of s, the input, multiplied by the transfer function h of s. So this has been discussed earlier, but I wanted to summarize this at the end so you understand exactly how this allows better manipulation of output calculation from the input, particularly when you go into frequency domain.